All right, so in the last video, I left you with this example. Did you notice anything strange about it? So first, let's look at the pivot position. So we got one here and one here, but we don't have a third pivot position. But I also notice I have a row of zeros and it equals 1. All right, so what is this last row telling us? This last row is telling us that 0 times x1 plus 0 times x2 plus 0 times x3 equals 1, which is saying that 0 equals 1. It's not true. All right, so that means we're never going to find a solution to this system because the system is inconsistent. So we would say, actually, there's no solution here. This is an inconsistent system. All right, so how do we know if we're going to have an inconsistent system or not? So remember, we're inconsistent if we don't have a solution, consistent if we have one or infinitely many solutions. So we actually have a theorem about this. It's called the existence and uniqueness theorem. So we're going to go over that right now. So note that this theorem has a name. It's not just theorem 1. So whenever you see a theorem with a name, that means it's important and you'll need to either remember it or know exactly what it says. Okay, so here's the statement of the theorem. We are going to assume a linear system is reduced to row echelon form. So not even reduced row echelon form, just row echelon form. That system is consistent if and only if, so this is my shorthand for if and only if, there is no row of the form All right, so we know that our system is going to be consistent if and only if we don't have a row that looks like this. A bunch of zeros equal to a number that's not 0. So if we see this, it's not going to be consistent. All right, so if a system is consistent, then we have the following things we already know. Number 1, there is a unique solution. Meaning that we don't have any free variables. All right, just like this example we saw here, there were no free variables, so we were able to get a unique solution, exactly what x1 and x2 are. Okay. Number 2, if a system is consistent, then there are infinitely many solutions. And when there are infinitely many solutions, we definitely have free variables. All right, so this is the theorem, and I think it's best expressed in like a little flow chart. So we'll put together a flow chart, and then that will be where we end for this section. Okay, so at the top of our flow chart, let's say we have a linear system at the top of our flow chart. All right, and our linear system can go in one or two ways. It can be consistent or not consistent. So if what our theorem says, all right, one option is that we have no rows that look like this. Okay, so we look at our augmented matrix, we don't have any rows that has zeros on one side, a number that's not zero on the other side when we are in REF. Or we do have that situation. Zeros set equal to something that's not zero. All right, so these are the only two options, consistent or inconsistent. All right, so if we are inconsistent, then we know we're going to get no solution. But if we are consistent and we don't have a strange row like this, then we have two more options. One, maybe we don't have any free variables. And when we don't have free variables, how many solutions will we have? No free variables means we're going to have a unique solution. All right, back up here, we're consistent. We could have had free variables. All right, and when we have free variables, we know we have infinitely many solutions. And these are the only three options. Unique solution, infinitely many solution, no solution. All right, and so that is the end of this section.